Hey everybody, this is Mr. Oliver again. I'm going to be going over the AP Physics C Mechanics Unit 4 review practice. This will be for problem number 1. Let's go ahead and get started. On this problem, we've got a situation where we've got a projectile being launched from this little cart. And currently the cart is locked in place, so it cannot move. Now it does say that the projectile leaves at a speed of v0 at an angle of theta, and the projectile will land over here at point P. The first question says to derive an expression for the time Tp at which the projectile reaches point P. Express your answer in terms of V0, theta, and physical constants as appropriate. So there are several different ways to do this, but anytime I talk about a total time of a projectile, I just need to think about the time it takes to go up to its highest point and then down back to its lowest point. And so in this case, since the beginning position and the lower position are essentially the same, it says assume the starting height of the projectile above the ground is negligible. Okay, so that means that the time to get up is going to be up to this highest point is going to be exactly the time it takes to get down to the lowest point. So all I really need to do is find the time it takes to travel up to its highest point. And that's easy enough if you use kinematics. If you think about it, this projectile has an initial speed at some kind of an angle, but only the vertical component is what gets it up in the air. So v0 sine theta is the initial component that launches it vertically into the air. So if that's true, then what I can do is find the time it takes to launch a projectile straight up with an initial speed of v0 sine theta, travels to its highest point where its final speed will be 0, and the time it takes will be determined by how much the acceleration is. In this case, it's going to be accelerating downwards at an acceleration of g. So I'm just going to use this kinematic equation right here. V is equal to v0 plus at. I'm going to make my substitutions. My final velocity will be 0. My initial velocity in this vertical direction is this v0 sine theta. My acceleration is negative g because it's going downwards opposite to the direction of the motion times t. And so the t is just v0 sine theta divided by g. Now that'll be the time to go up, and so that'll be the time it takes to get to this midway point at its highest point. And since it's symmetric, the time it takes to go down is going to be twice this amount. So our expression for Tp, time to get to point P, is 2 times v0 sine theta divided by g. Okay? And when it says to derive a function or derive an expression, you need to go through all these steps, as well as maybe illustrate kind of what you're talking about in terms of v0 sine theta, etc., to get full credit. So make sure you're showing all of your work here to get full credit for A. Now question B has us sketch a couple of graphs. Now this was pretty easy because if you remember, for a projectile, in the horizontal direction, the velocity is constant. So as this thing flies horizontally, that velocity in the x direction is a constant value. Okay, and if you remember, the horizontal component VOX is equal to the horizontal velocity Vx, which is just VO cosine theta. And so that value right there, like I said, is a constant velocity. All right, so when I sketch this over here, all I have to do is draw a horizontal line from time 0 to Tp, and I also need to label this as VO cosine theta. It is critical that you label it because it says explicitly label the vertical intercepts. Okay. Now, in the vertical direction, the velocity in the vertical direction changes with time. It starts off with an initial velocity VO sine theta. That's my initial velocity, so that's where I'm going to have to start, at VO sine theta. The projectile goes up in the air, and so it stops momentarily in the vertical direction. It's still moving side to side, but it's at its highest point, it stops. So that means that midway to the total time, you're going to have a velocity of 0. And then on the lowest end, when it hits P, the velocity in the vertical direction will be exactly the opposite of the velocity in the vertical direction when you start. And so you get a linear function between time 0 and time TP. And if you wanted to make some kind of additional comments, it doesn't ask you to in this case, but you would say that the slope is equal to negative g for that function. All right. Now question C. Oh, by the way, guys, this is worth 5 points. So a lot of times in these free response questions, you get a whole bunch of little individual things, but sometimes the graphs are probably worth more than anything else because they illustrate a whole lot of information. So make sure you spend some time doing the graphs. It's going to pay off for you. All right, question C is now pertaining to a new situation where they remove the little supports that keep this cart from moving. And it says that the cart has an initial speed v1. So it's already moving with a speed v1 to the right here, v1. The projectile again leaves the cart with speed v0, so it's still launched in the same condition that it was before, at the same angle. But this time the projectile doesn't go all the way to P, the projectile just kind of lands short. And so you need to, in part C, give a physical reason why the projectile lands at Q, which is not as far from the launch position as P, and explain how that physical reason affects the flight of the projectile. So the way I said it is that the rightward velocity as this cart moves to the right essentially takes away from the leftward velocity, this v0 x going to the left. So it's kind of like a relative motion problem where if you have a velocity v1x going to the right and a velocity v0 x going to the left, that the net overall velocity in the x direction will be less. And so in words, I said the rightward velocity v1 will cause the initial launch velocity with respect to the ground with respect to the ground to be less than when it was stationary. All right. And so, therefore, it's going to land at a shorter distance. Therefore, it travels a shorter distance. All right. And that was only worth 1 point, but in question D, it actually asks you to do some mathematics with that kind of concept. And so what I said is that the distance that this projectile travels, in this case a distance d, is equal to the velocity in the x direction times the time. Okay, so we already know what time it's going to take because the time doesn't depend on the horizontal motion. The time only depends on the vertical motion, and nothing there has changed. Everything, the angle's the same, the v0 is the same, everything's the same. So we already know what the time was. That's this time to p. It's not going to change anything. However, the velocity in the x direction is different. In this case, the velocity in the x direction is the difference between this horizontal velocity going to the right and the initial velocity in the x direction going to the left. So Vx is equal to VO cosine theta, and I'm assuming Vx is going to the left because this projectile is launching to the left. I'll call that a positive direction. So I've got VO cosine theta minus V1. All right? So this is our velocity next term. Our TP is our time. And so I can make those substitutions. So D will equal VO cosine theta minus V1, that's my velocity in the x direction, times my time, which is 2VO sine theta divided by G. All right, sorry guys, I'm off the page there. So all I did here is I substituted in this term for Vx right there, and I substituted in the time term 2V0 sine theta over G. And now all you need to do is take that expression and solve for V1. And when you do that, you come to the solution that V1 is equal to VO cosine theta minus G over D, there's a little bit of algebra in there, divided by 2 V0 sine theta. All right, and that's your solution for D. And guys, if you have some other kind of solution that did solve for V, but this looks different, as long as it's mathematically equivalent, you're fine. You don't have to substitute and reduce, make everything look the same. Just as long as you solve for V1 in an appropriate way. That's all you need. Okay, so in answer or question E, it tells us that after the launch, there is the cart speed is V2. All right, and so that means the cart is moving to the right at a speed of V2. Beginning at time t equals 0, the cart experiences a braking force of negative BV. So there's this braking force going to the left, negative BV. And so this is kind of like a drag force kind of problem. All right, so what's going to happen is this cart is going to start with its initial speed at this position, and it's going to travel some distance until eventually it stops. So the final velocity here, of course, will be 0. Now, the first question says, using Newton's second law, write, but do not solve a differential equation that represents the motion. Okay, so that's pretty easy. When we write differential equation, it's just an equation that has a derivative. And it even tells us to say using Newton's second law. So I'll say F is equal to ma. Well, what is that force? Well, that force is negative BV. And that equals ma. And if you remember, to make a differential equation, we need to make a substitution to have a derivative, and that substitution is going to be for acceleration, which is just dv dt. And that's your differential equation. That's all you have to do. Now on question II, it does say to show that the speed vt of the cart is a function of time by the equation vt equals v2 e to the minus bt over m. And so basically, essentially what we're doing is we're going to solve this differential equation. Okay, so that's all we're going to do in this next step. And guys, if you're not comfortable with solving differential equations, just skip that step. I think a lot of times that you get to this point and you think, oh, I have to do this. Well, if you've still got another question to work on, I would just skip it and move on to the next one. Don't kill yourself if you're not comfortable with doing that. Everybody's calculus skills are in a different place. And since we didn't get to spend time in class going over how to solve these things, unfortunately, you probably even missed it in your calculus class. So I hope that they're not going to have that kind of question on the AP exam, but we got to prepare for it anyway. So let me show you how to solve that. Okay, so it's really not that difficult. So we'll start off with what we had written in the previous part, minus b over m times v, and that equals, I'm rearranging a little bit because I moved the m over to the left, that will equal dv dt. And so the way we solve this is to separate and integrate, which just means I'm going to get all the terms that are associated with velocity to one side of the equation and all the terms associated with time to the other side. And so there's some calculus reasons why we can do this. I'm just going to kind of multiply by dt to get it over here to the left, and then I'm going to divide by negative b over m times v to get it over to the right. And so what we're left with is dt is equal to negative m over b, or actually no, let me just yeah, we'll just leave it as is. We'll have dv divided by negative b over m times v. Okay, so I can kind of rewrite this. In fact, let me switch this around. I'm just going to swap sides. It's okay just to move this to the other side. Typically, I like to put the time term on the right. And also, I'm going to move this fraction around so it looks a little bit better. So we'll have minus m over b times 1 over v dv. Okay, because dv is on top, you're multiplying by dv. The v is on the bottom, it's a 1 over v. And then this fraction that's on the bottom, it actually belongs on top, but you got to flip it. And so that's all I did with this. I just kind of rearranged this right-hand side. And I'm going to set that equal to dt. All right, so that's kind of the separate step. We took it apart, rearranged it, just kind of made it look good. And the reason why I brought this negative b over m out in front is because it's a constant term. It really doesn't play into this velocity here. So the next step here would be to integrate. So I'm going to integrate both sides like so. And the limits of the integration are a little bit tricky. So on the time, we started at time 0. And then later on, we're going to get to some later time. What is that? I don't know. So let's just make it a variable, t. All right. So those are our limits of our time. Now, at time 0, there was an initial velocity for this cart. It said when it started off, the cart was moving at a speed v2. So that's our initial velocity. But later on at this arbitrary time t, we don't know what the velocity is. And in fact, it's going to be some velocity that is a function of that time. So that's why I make this quote unquote final velocity, this upper limit, this function vt. If I had actual numbers, I could just plug a number in there, but I don't. So now what I need to do is integrate both sides. Well, on the right, this is really simple. The result of this will just be time t. On the left-hand side, you're going to get minus m over b times the natural log, because what we have here is 1 divided by v. The integral of 1 over v is the natural log of natural log of v, sorry, evaluated between v2 and the function v of t. All right, so when I do this evaluation, I don't just plug numbers in. Remember, I got to do fundamental theorem of calculus. And so we'll have natural log of v of t, so that's plugging in our upper limit, minus the natural log of v2. And all that is still multiplied by this negative m over b out here. On the right-hand side stays the same. Now right here, I've got this natural log of something minus natural log of something. If you remember your log rules, you can rewrite that as a ratio. So I can write that as natural log of v of t over v2. All right. And something else I'm going to do here is I'm going to go ahead and move this over to the right-hand side by flipping it around. So that'll equal minus b over m times time. So I just move that over to the right-hand side. Now, I need to solve this for v of t. All right. So how do I get rid of a natural log? Well, I take the exponential of both sides. And on the left-hand side, those will cancel out. And then the last thing I need to do, because all these parentheses are kind of gone now, I need to move the v2 over to the right-hand side. And so finally, we come up with a solution. V of t is equal to v2 times e to the minus b over m t. And that is our classic exponential decay kind of function. All right. If I were to graph that, you would see that we started off at v2, and over time our velocity approaches 0. Now, does it ever theoretically reach 0? No, it doesn't. It's an asymptote to 0. In reality, it does stop. But for our mathematical model here, it's approximated by this function. Okay, so that's the second part. That's II. That's E part II. And so the last part asks to derive an expression for the distance that the cart travels from t equals 0 until it comes to a stop. All right, so for that one, what we need to do to find distance, we're just going to use some classic understanding of kinematics, that the distance is equal to the integral of the velocity function with respect to time. Well, I'm given the velocity function right here, so I just need to take the integral of that using the appropriate limits and solve for the distance x. Technically, it's not the distance, it's the displacement, delta x. And so we'll do that on this last page. Delta x is the integral of the velocity function with respect to time. Now let's go ahead and figure out what our limits are. We're going to start off at a time of 0, and then it theoretically doesn't stop at all, but if I let it approach an infinitely long amount of time, yeah, it'll stop. So my upper limit has to be infinity. All right, so setting our limits from 0 to infinity, and we're going to take the integral of our function that we're given, v2 e to the minus b over m t. Now I can pull out the v2 because it is a constant. And we're taking the limit of e to the minus b over m t. Now if you can't remember, just remember on your equation sheet it has a bunch of these integrals, and this is of the form e to the ax. And so the integral is 1 over a e to the ax. All right. So in this case, our a term is this entire term in front. A is equal to negative b over m. All right. So when we take that integral, we'll have v2 times the integral. Not times the integral. We've already figured that out. V2 times negative m over b, and why it's flipped upside down is because it's 1 divided by that. It's an inverse, times e to the minus b over m times the time. And we're evaluating that between 0 and infinity. Those are our limits. Now, you can't just eliminate one of these because, exponential functions, that kind of weird. I will say I'm going to go ahead and pull out the negative m over b out front. So I'll have negative m over b times v2, and I'm evaluating this integral of e to the minus b over m, evaluated at this upper limit, will be to the infinity, minus e to the minus b over m times 0. Now, 0 times anything is going to be 0. So we're taking e to the minus 0 or e to the 0, and so that means that this lower limit will evaluate to 1. And when you take e to a negative, really big number, this is 0. Right? So our total final answer is going to be minus m over b times v2 times 0 minus 1. And so all that means is you're multiplying by negative 1. And so this minus sign goes away. And so your solution for your displacement is equal to m over b times v2. Okay. And guys, like I said, there's a lot of calculus in that, but it's a good exercise to go through this maybe 2 or 3 times in case there is a differential equation that you're asked to solve. So please, if you would, spend some time with it. And if you have any questions, please let me know. Thanks a lot, and I'll talk to you later. Bye bye.